Hello, so this is a revision video for AP Chemistry 5.11, Catalysis. A catalyst is a substance that speeds up a chemical reaction without being permanently changed or consumed. Catalysts work by providing a new reaction pathway that has a lower activation energy barrier than the uncatalyzed pathway. This increases the frequency of effective or successful collisions between reacting particles and makes the reaction proceed faster. Catalysts can work in many different ways, but they usually introduce a new elementary step in a reaction mechanism, and this introduced step involves a new temporary intermediate that includes the catalyst. The overall net concentration of the catalyst remains constant throughout the reaction. The catalyst is often used up in an early step but regenerated in a later one, meaning overall there's no change in net concentration of the catalyst. The rate-limiting step is altered to have a lower activation energy pathway. Reactants bind to the catalyst or interact with it in such a way that causes this decrease in activation energy. The catalyst may help orientate the reactants in a particular way or stabilize a high-energy transition state. Exam tip here: if you're trying to identify a catalyst in a reaction, always look for a reactant that gets used up in one step and produced as a product in a later step. Unlike an intermediate, a catalyst will be present at the start of a reaction and at the end, which is why it isn't included in an overall reaction equation. An intermediate isn't present at the start of a reaction, it is produced during the reaction and then gets used up before the end of the reaction. Catalysis refers to a reaction where a catalyst is being used or a reaction is catalyzed. There are several examples you need to be comfortable with for AP Chemistry. Enzyme catalysis is where enzymes are used. Enzymes are biological catalysts made up of proteins that have active sites. The active sites have complementary shapes that a substrate, biological reactant, can bind to. The binding reduces the activation energy barrier for the overall reaction, allowing it to occur at lower temperatures. Enzyme catalysis is essential for nearly all biological processes. Acid-base catalysis occurs when a reactant gains or loses a proton, a H+ ion, to form a new intermediate. This allows the reaction to proceed through new elementary steps. For example, the decomposition of hydrogen peroxide. The overall reaction is 2H2O2 goes to form 2H2O plus O2, and a H+ catalyst is used. The H2O2 and gains a H+ ion to form H3O2+ in the first step, and then this unstable H3O2+ intermediate breaks down into water and an oxygen molecule. H3O2+ goes to form H2O plus O2 plus H+. Note here that the H+ ion is regenerated at the end, meaning we can consider it to be a catalyst. So the overall reaction would be 2H2O2 goes to form 2H2O plus O2. Surface catalysis, which is an example of heterogeneous catalysis, occurs on a solid surface, often a metal. Reactants adsorb onto the surface, where bond breaking and bond making occurs. A new set of intermediates is formed on the surface of the catalyst before the products diffuse away from the surface. Note it's also referred to as heterogeneous catalysis because the reactants are in a different phase to the solid catalyst, usually gaseous or aqueous reactants. The energy profile for a catalyzed reaction will have a lower overall energy barrier, a smaller activation energy. However, it will show the same energy difference between reactants and products overall, because catalysts don't change the thermodynamics of a reaction, meaning they don't change the overall energies of reactants and products. Only the kinetics, so how quickly the reaction happens. So the overall difference in energy between reactants to products will always be the same regardless of whether a catalyst is used. The only difference is the activation energy in the reaction profile diagram.